Hi guys, we're going to get into the topic of alkene and alkyne nomenclature. The nomenclature here is mostly similar to the alkane nomenclature with a little bit of a difference due to stereoisomerism, and I'll talk about that in just a moment. So alkenes are hydrocarbons that have a double bond. So let's recall just our hydrocarbons. We have a few classes here. We have our alkanes. Those are saturated with carbon-carbon single bonds only. And those have a molecular formula, general molecular formula, CnH2n plus 2. Then we have our alkenes, and those are going to have at least one double bond. So there's an example of an alkene. Our alkynes have at least one triple bond. And then the last category of hydrocarbons that we mentioned are aromatics. And remember, we can sort of abbreviate the fact that there's resonance within that ring structure with a circle. So those are 3 hydrocarbons. We already did naming for alkanes, and today we're going to do alkenes and alkynes. The double bond in an alkene is rather reactive. We will learn about a lot of reactions later in the semester that are additions to alkenes or reactions of alkenes. And the reason that is because you have a pi bond that's perpendicular to the sigma bond. So looking at this slide on the left here, we have the sigma bond. So one of these bonds is always going to be the single bond. And then the other bond is the pi bond. So in this particular molecule here, I would have 1, 2, 3, 4, 5 sigma bonds and 1 pi bond. The pi bond happens from an overlap of the electrons in the p orbital. So remember that when we hybridized our atoms, we would, for carbon, originally have, I'm going to skip the 1s, I'm going to draw the 2s and the 2p. For carbon, normally you'd have, if this is by potential energy, and this is my orbital diagram, for a carbon atom, I have 4 valence electrons. I would have 2 electrons in the 2s and 1 valence electron in each of the 2p orbitals. Because it's more stable to have electrons, because it's more stable to have orbitals that are half filled, one of these electrons will be promoted to the 2p orbital. When the atoms hybridize for an sp3, all of these are used in hybridization to make an sp3 because we have 3 of our p orbitals and 1 of our s orbitals that are used. But when you have a double bond with a steric number of 3, what's happening is we're using 1 s orbital and 2 of the p. Again, that's s, 1s, p, 2 of the orbitals from the p. Our hybridized orbitals are going to look like this. So I'm essentially going to have 3, you know what, let me draw this a little bit lower. The energy here is going to be somewhere between the 2s So this is our sp2, and then there's still that 2p orbital that has one electron. So again, I hybridized the 3 orbitals that are circled there to have 3 sp2 orbitals, and then there's still that electron in the 2p orbital. When we have pi bonding, one electron that's in the p orbital on one carbon atom pairs up with an electron in a 2p orbital on another carbon atom, and it's shared. So sort of overlap here in this back orbital, we'd end up sort of seeing a situation like that. So we have overlap of the 2p orbital. The 2p orbital is going to be perpendicular to the sp2 orbitals. Again, this is showing that, and we have the overlap here with one electron from one carbon and one electron from the other carbon. These are our 3 sp2 orbitals that we're using to hybridize, which are again these right there on the right. Just to help you recall here the hybridization of something that has a steric number of 3 is sp2. The bond angles are 120 degrees and the molecular geometry is trigonal planar. Here again, the unhybridized p orbital with one electron will overlap, forming the double bond. So it turns out that double bonded molecules with double bonds have bonds. The double bond is shorter than the single bond. That's because when we think about what's happening with an sp3 versus an sp2 versus an sp, the sp3 orbital is going to be 25% S and 75% P character. For sp2, it's going to be 33% S and 66% P character. For an sp in a triple bond, this would be 50% S and 50% P. The p orbitals look like a dumbbell. This would be a p orbital, the shape. And the s orbital is more like a sphere. So when you have more s character, the bonds are going to be shorter and they're going to be stronger. So as we can say that these are going to be longer bonds for sp3. These are going to be shorter bonds for sp. And then sp2 is somewhere in between. If I want to think about the strength of these bonds, I can also think of the triple bond sp hybridized carbon as being a stronger bond. You can also sort of think about it as sp, if it's a triple bond, is almost like 3 bonds. So when we have sp molecules, those are going to be our alkynes, which we're going to name. Our sp2 are going to be our alkenes, and our sp3 are going to be our alkanes. Let's skip over this one slide here. When we have alkanes, we have only single bonds. You guys already know that there's free rotation around single bonds, and I showed you that in class, and that's why we were sort of looking at the Newman projections. So you can rotate around a single sigma bond, but there is no free rotation around double bonds. That's because you have overlap in the y-axis as well. So we have to tell the reader what type of a double bond I have. Do I have a cis or do I have a trans double bond? So I want to sort of go over this and then clarify one of the confusing terms. So if I have an alkene, let me just draw this again differently. Oops. Okay, so if I have my alkene on the left, when I'm looking at this double bond, I'm going to put a circle around where the double bond is, and I'm going to put a circle on this double bond. The one on the left is a trans alkene. The R groups are on opposite sides of the double bond. You can probably see that one is going up, one is going down. On the right side, my R groups are on the same side of the double bond. So I can call this my cis alkene. I'm sorry, totally wrong. This is my trans alkene, opposite sides. And this is my cis alkene. I want to differentiate this from ring compounds. So we have our cyclohexane. There is cis and trans in alkenes. This has to do with what side of the double bond it's on. So in alkenes, cis and trans is about what side of the double bond it's on. In a ring, cis and trans is on what side of the ring? And this means something different. So this is more like cis and trans is going to be up or down. If I have this cyclohexane, if I have this cyclohexane, I have a chlorine. Remember that the wedge always means up. The wedge is up, and the dash is down or away from you. I have a chlorine that's up, and I have a methyl that's down. So this would be a transalkene. If I put this alkene into a ring, well, let's do a couple of things with this cyclohexane real quick. Let me go ahead and give it numbers. At carbon number 1, I have a chlorine. At carbon number 2, I have a methyl. So this is 1-chloro, 2-methyl, cyclohexane. And again, I have one up and one down. Those are on opposite sides of the double bond, so that's a trans. That is different than when we're talking about with the alkenes. So alkenes, it's about the side of the double bond. If you guys needed me to do this, let's just go ahead and I'll go ahead and draw a chair structure and then the ring flip just so you guys see this again. I'm going to go ahead and number my carbon atoms. This is 1, this is 2, this is 1, this is 2, 3, 4, 5, and 6. And I have a chlorine that needs to be facing up. So that's going to be axial on my left chair. And then I have a methyl that's going to be facing down. That needs to be down axial on my position 2. Then on the right side chair, I still need my chlorine to be facing up. So remember, when you do a chair flip, everything that's axial goes equatorial and vice versa. So my chlorine, again, still going to stay in position up, but now it's equatorial. And then, oops, over here, sorry guys, I put a Cl, it's supposed to be a CH3. Then on position number 2, it should be facing down, but equatorial. So a little bit smashed here, but this is different than on the double bond. So if I have a molecule that is an alkene that has 2 groups on one side of the double bond that are equivalent, like this. So the methyls, I have 2 methyls on the left side of this double bond. In this particular case, there's no cis or trans. That's because there's nothing for me to compare. I would be looking at the position of the left atoms relative to that blue one, but they're the same, so it doesn't matter. So if you have 2 of the same groups on either side of the double bond, there's no cis or trans. For naming alkenes, you're going to find the longest continuous chain, and similar to alkanes, you're going to find the longest continuous chain. So I'm going to circle the carbons there. No, let me move this. Sorry if you already did that. Let me move this to here. Whoops. To here. Okay, so I found my continuous carbon chain. That's 2, 4, 6 carbon atoms. So instead of being hexane, this is going to be hexene because it's an alkene. And then how do I number it? So please remember this very important rule. You're going to number the chain so that the double bond has the lowest number. That means you're going to number closest to the double bond. So when I number my atoms, this is carbon number 1, 2, let's get a darker color here. 1, 2, 3, 4, 5, 6. With alkenes and alkynes going to have the same rule. You are numbering closest to the double or triple bond. Now I'm going to tell the reader the position of where my double bond starts. My double bond starts at position number 2 and it goes to position number 3. So this is going to be a 2-hexene. This is going to be a 2 hexene. That's going to be the parent chain, 2-hexene. I also need to tell the reader that at carbon number 4, I have a chloro, and at carbon number 5, I have a methyl. So this molecule is called 4-chloro, 5-methyl, 2-hexene. And now I need to tell the reader if it is cis or trans. So when you have a double bond, don't forget to add the cis or trans. In this case, I'm looking at the groups attached to my double bond. They are on opposite sides of the double bond. So I would call this trans. We're going to actually get into another numbering system or another naming system. So just in a minute, we'll get to it. This is E. This is E, more appropriately named as E. So that you guys know, there's old IUPAC and new IUPAC rules. So for this molecule, this 2-hexene, the new IUPAC rules are, instead of calling this blah, 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 5-methyl 2-hexene, sometimes you'll see this as 5-methyl hex 2-ene. Both are correct. Old system, new system. If you have a ring with a double bond, it is implied that carbon number 1 is where the double bond starts. It is always where the double bond starts. So that would be carbon number 1, 2, 3, 4, 5, and 6. You'd be making your way to the other molecules. And so this would be a cyclohexene. And then at carbon number 3, I have a chloro, and at 4, I have a methyl. So this is going to be 3-chloro, 4-methyl, cyclohexene. Sorry, that got kind of smushed there. If I was redrawing this from the name to the structure, what I would want to do first is just draw a cyclohexane, put a double bond anywhere, and call that carbon number 1. And I would just 1, 2, 3, 4, 5, and 6. And then I would add my substituents or my branches to the appropriate location. So I'd have my chlorine at carbon number 3, and I'd have my methyl at carbon number 4. If you have multiple double bonds, you are going to convert this into a diene or a triene or a tetrene, and you're going to tell the reader where all of the double bonds start. So if I had this molecule, let's say this one, this would be carbon number 1, 2, 3, 4, 5, 6, 7, 8. This would be octene, but I would convert this to octatriene, octatriene, and I'm going to tell the reader at carbon number 1, I have a double bond starting. At carbon number 3, I have a double bond starting. And at carbon number 5, I have a double bond starting. So it would be 1, 3, 5, octatriene. Here's some more examples as cis-trans isomers. So the type of isomers that are cis and trans on opposite sides of the double bond, we had our constitutional isomers. Constitutional isomers were same formula, different atom-to-atom connectivity, that was one type of isomer you guys learned about. What we're learning about here are stereoisomers. So stereoisomers have different arrangement in three-dimensional space. We're going to talk about other stereoisomers in chapter 5. Some of you who might have tried organic chemistry before, these are going to be our RS isomers, our one type. Another type is our cis-trans isomers. These cis-trans isomers, we call these geometric isomers. So looking at these four possibilities, these are all some of these are constitutional isomers and some of them are stereoisomers. So for these two, the relationship between these two, these are stereoisomers. We have the same, oops, no, not those, totally wrong. Let me go back and redo that. Sorry, it's not those guys. I don't know how to erase once I've done this on here. No, that's not erasing. That's making it bigger. Well, sorry, not those. It's these two. These two are stereoisomers. Okay, so for this carbon right here, I have a methyl and a hydrogen attached. For this carbon right here, I have a methyl and a hydrogen attached. On the right one, I have a methyl and a hydrogen, and on the left one, I have a methyl and a hydrogen. These are stereo. Same atom-to-atom connectivity, but a different arrangement in three-dimensional space. These are all constitutional isomers of each other because this carbon atom is connected to one methyl, one hydrogen, on the other side, one methyl, one hydrogen. Compared to the top, I have two hydrogens on one side, and then I have a carbon and an ethyl. So you can probably see how these are constitutional isomers. There's a different atom-to-atom connectivity. Again, constitutional isomers. But these are the stereoisomers. So same atom-to-atom connectivity, different arrangement in three-dimensional space. Oleic acid is the oil. It's olive oil. It's an olive oil. It's one of the fatty acids in olive oil, and it has a single double bond. It's a mono unsaturated. And all natural unsaturated fats are going to be cis. That's just how they are. It creates a kink in them and it makes them more liquid at room temperature. So cis and trans is kind of a simple way to indicate whether something's on the same side or opposite side of the double bond. But then there's something like this one where it would be a little bit hard to tell. So what we have to do is we have to briefly go over the Ingold pre-log system. And what we're looking at here is bigger atomic number. So the atom that has the biggest, fluorine has atomic number 9, hydrogen is atomic number 1, iodine is atomic number 53, chlorine is atomic number 17. When I'm going to use these rules, I'm looking at priority based on largest atomic number. I'm going to kind of split the double bond, and I'm going to look at the left side and the right side of the double bond separately. On the left side, I have number 17 and number 53, iodine wins. On the right side, I have number 9 for fluorine and number 1, sorry, that's a 1 for hydrogen. Fluorine wins. So this molecule is a trans, opposite side of the double bond, but when we can't say it's simple cis or trans because there's a lot of other atoms attached, we use a different nomenclature system, E and Z. E and Z. E is opposite side, and Z, zusammen, is same side. And you can remember Z as Z, same, side. When it's Z, it's the same side. So if the iodine and the fluorine were on the same side, it would be Z same side, that would be a Z. But it's on opposite sides. So this is E. Again, here's another example. So priority number 1's up here, Z same side. Second one, priority number 1's opposite sides, E, entigen. Again, I'm looking at atomic number here. So the atomic number of iodine is bigger than bromine. Again, I'm splitting the molecule. I'm looking at iodine versus bromine. Iodine wins. Left side, I'm looking at fluorine versus hydrogen. Fluorine wins. This is Z same side. This is Z. We're going to use the Z and the E when we name our molecules. We're going to put it in parentheses. If you're typing it, it's also in italics. Now, we have to think about if we have something. Let's say this one and all right. If I look at the left side of the molecule, again, I kind of want to imagine splitting my double bond and trying to figure out what's going on here. Here I have a CH2. Here I have a CH3. So my carbon is the same. 2 of my hydrogens are the same. And then there's another hydrogen. On the left side, I have a CH2 and then I have a chlorine. That atomic number is bigger than the second hydrogen. So let me kind of like write this out real simple here. This would be like a C, H, H, H. This side, I'm going to kind of make it even simpler, would be like a C, H, H, Cl. The carbon is the same, two of the hydrogens are the same, and what it comes down to is comparing hydrogen and chlorine. Chlorine wins, so this side at the top wins. Down here, I have a CH2 to a carbon, a CH2, and then I have a CH3 here. Here I have a CH2, that's the same, but then it goes to an OH. The atomic number of oxygen is 8. The atomic number of carbon is 6. Oxygen has a bigger atomic number. We're going to circle this side. So if I was determining whether this is Z or E, this is opposite sides of the double bond. So this is an E isomer. For this one, when I'm naming this one on the left, again, I'm just looking at the longest chain. So let me draw it down here again for you guys. I'm looking at the longest chain. This is probably what it would look like on your paper. I imagine splitting double bond here. Let me determine if it's E or Z. The bromine has a bigger atomic number than chlorine, so that wins. And remember, there's a hydrogen here. Carbon wins because it has a bigger atomic number, so I know that this molecule is going to be E. But let me name it. I need to name it as an alkene. That's carbon number 1, carbon number 2, carbon number 3. This is a propene, 1 propene. And then also at carbon number 1, I have a 1 chloro and a 1 bromo. This is going to be 1 bromo, 1 chloro, propene, forgot to put the 1 in there. 1 propene. And now I tell the reader that it's the E isomer. It's the E isomer. Thinking about another topic here is stability of alkenes. It turns out that because of something complicated called inductive effects that you don't need to worry about all that much, stability of alkenes is dictated by the substitution of the double bond. Okay, so if I have just ethene, turns out that that has the highest potential energy, meaning the least stable. Down here is the most stable, lowest potential energy. Experiments were done to determine that the ethene is the least stable alkene, then it's a monosubstituted, then it's a disubstituted, a trisubstituted is more stable, and a tetrasubstituted is the most stable. You should also know that in terms of stability, the trans is more stable than the cis. So that means the potential energy of the cis is higher than the potential energy of the trans. If I gave you a bunch of alkenes, if I gave you a bunch of alkenes like this, and we thought about, well, what is the most stable? What you want to do is you want to label them. So this is, when I'm thinking about the substitution, I'm looking at how many carbon groups I have attached directly to the double bond. This is a di-substituted trans. This is also, I have 2 groups attached. This is a di-substituted cis. Next one is a 1, 2, 3 tri-substituted. Next one is a di-substituted but geminal. Geminal means on the same carbon. So you can see that this di versus the 2 other ones, this one is going to be less stable because there's no alkane group, or there's no R group on the other side of the double bond. So then going down to the bottom, I have 1, 2, 3, 4 attached. That's tetra. Then I have another one that's just a mono. Then I have another one that's just ethene. So if I put these in order in terms of stability, let me give them all a number. Let's say this is number 1, 2, 3, 4, 5, 6, and 7. I'm going to put them in order from least to most stable. The ethene, number 7, is the least stable. That's less stable than the mono-substituted one, number 6. Then we're moving to the di-substituted. Number 4 is less stable than number 1 and 2. We're going to look at the other di-substituted. So the cis is less stable than the trans. Then the tri-substituted one, number 3. Then the most stable one is number 5. So this is the stability of alkenes. And again, I'm just going to kind of skip over here because I already talked about this. So if you had this question between these three, which would be the most stable to the least stable? So A has di substituted. This is di cis. B is tetra substituted. C is tri substituted. So if I had to say which is the most stable, or which is the least stable, so we'd have the A, which is less stable than the C, which is less stable than the B. Which would be the most exothermic, the one that gives off the most energy? So most exothermic would give off the most energy, which would be the least stable. So which of these would be the most exothermic? The least stable one? This would be A. That would be the most exothermic. Given these energies of hydrogenation, which one? So this would be the least, the middle, and the most. The middle one would be the tri. So I can pair these up given the most heats of hydrogenation. This would be the negative 30.2. The tetra would be the negative 26.8. And the tri would be the negative 28.4. This alkyne slide is in the wrong spot. Sorry about that. And thinking about cyclic compounds with double bonds, so we kind of already talked about this for the most part. When you have trans cycloalkenes, they are not stable unless they are bigger cycloalkenes. So if they are 8 carbons plus. We're going to talk about this bicyclic Brett's rule. It'll come up again later on in the semester. But Brett's rule basically says you can't have a double bond at a bridgehead carbon unless it's a big molecule. So again, 8 carbon atoms. You can't have a double bond at a bridgehead. Here, this is not a bridgehead. This is bicyclic, but it doesn't have a bridgehead. Brett's rule is specifically about bridgehead. So Brett's is for bridgehead, bicyclic. Looking at these, which of these following are stable? This one is okay because you have a big ring system and you have the cis and you have the trans, but you have the cis. This is stable. In B, you have a double bond at a bridgehead carbon. This is not stable. Not stable. At C, you have a cis double bond and you don't have a double bond at a bridgehead carbon. This one is stable. This one's okay. In D, you have a double bond at a bridgehead carbon. However, the ring system is 8 carbons or more, so this one is stable. We are going to move on to alkynes. For alkynes, there are always going to be one triple bond or more in the molecule. And I'm going to just kind of give you an example of an alkyne. For alkyne naming, you always, just like with the double bonds, you need to start numbering closest to the triple bond. So I'm going to highlight my carbon atoms here. And again, I have to start numbering closest to the triple bond. There are 10 carbon atoms here, and I need to tell the reader this is a decane. In fact, this is a 2-decane or a dectuane. And then the name of the molecule, because I have a chlorine at carbon number 6, this is going to be 6-chloro 2-decane. With triple bonds, you don't have to worry about the cis and trans. Only double bonds. You have to worry about the cis and trans or the E and Z. For double bonds, for alkenes, you should use E and Z. So again, make sure you're starting closest to where the triple bond is. We talk about alkynes in 2 ways. We talk about them being terminal or internal. We'll talk more about this in chapter 9. But a terminal alkyne is with the triple bond at the end. An internal alkyne is with a triple bond in the middle. So we won't be naming things with other functional groups except when we get to alcohols, which is going to trump the triple bonds and the double bonds. But if you have a molecule with double bonds and triple bonds, so if you have like alkene, if you have a molecule, if you have a double bond and a triple bond in the same molecule, it would be classified as an alkyne, not an alkene, but it does have a double bond. In the naming, the alkyne would take preference. However, I am not going to test you on this. So you don't need to worry about that too much, but just to tell you, the alkyne would take preference over the alkene. Alkenes and alkynes are similar to alkanes. Physical properties of them are they are generally insoluble in water, they are generally nonpolar. They're going to be mostly soluble in organic solvents because we have a lot of carbon-hydrogen bonds here, a lot of dispersion forces. Oftentimes they're going to be less dense than water. So maybe you've seen oil or gasoline go on water. That's a lot of hydrocarbon. It is going to be less dense than water. That's why you see it on the top. And up to 4 carbons, they would be gases at room temperature. And that's the end of the nomenclature of this. I hope this was helpful.